根据条件虽然不大。
他去他那个写个报告。
Yeah.
Okay, so today we are happy to have Artan talking about theory of nested Hilbert schemes on surfaces.
Thank you. So, thanks for having me here. This is the second time I'm giving a talk in the CMSA, and it's great to be here again. So this is about joint work, first of all. I mean, joint work with Amin Gholampour, who is at University of Maryland, and Professor Yao, Shing-Tung Yao. And we just put the papers on archive, so we have put 2 papers on there. The one I'm talking about today is about the theory, developing a theory over surfaces. This nested Hilbert schemes I will talk about today, what kind of spaces they are. This is talk today is originally a twofold theory. And then tomorrow I'm scheduled to give a talk, second sequence to this, in differential geometry conference in the math department, where you can see an application of this twofold theory for threefold geometries. And actually, I should say that originally when we started thinking about this, we were trying to calculate some invariants for threefolds, and we realized we need to understand these spaces. So before talking about nested Hilbert schemes, let me talk about Hilbert schemes themselves. So Hilbert schemes on surfaces. Let S be a non-singular projective surface over complex numbers, then for any positive integer m and effective curve class, so for me bigger than or equal to 0 means effective curve class beta in the second integral cohomology of this algebraic complex surface denote S of bracket m beta to be Hilbert scheme of one-dimensional subschemes Z in S, all right, where fundamental homology class of Z is equal to beta and second Chern class of ideal sheaf of Z is equal to M. So given this information, we can construct a Hilbert scheme. If you're a differential geometer or a physicist and so on, ideal sheaf, whenever you have in algebraic geometry, there is a one-to-one correspondence between the spaces, the schemes, and so on, and functions defined on them or functions vanishing on them. And ideal sheaf really means that you can look at the sheaf of regular functions or holomorphic functions on this algebraic surface, and you can restrict those things to functions holomorphically defined and supported on the subscheme itself via restriction, and the kernel of this map gives you satisfies the property of being a sheaf. It's a pre-sheaf, it has gluing property, it's a sheaf, and we call that ideal sheaf because it's an ideal in the corresponding algebra over which the sheaf theory is defined. It's the coordinate ring of the algebraic right. So that's what the ideal sheaf is, and with this data we can construct a Hilbert scheme. Now Hilbert scheme parameterizes ideal sheaves of subschemes. Now some remark, if when beta is equal to 0, we will be talking about Hilbert scheme of points only. SM is a smooth variety of dimension 2m. This is the work of Mukai, and many others have confirmed this. And when m is equal to 0, so this is a specialization of the Hilbert scheme of points and curves to Hilbert scheme of points or Hilbert scheme of curves. When m is equal to 0, which is when we get the Hilbert scheme of curves, this object is in general singular, unless our cohomologies I bigger than or equal to 1 cohomology of L's vanish for any line bundle for any L on Picard of S, the line bundles on S, where first term class of that line bundle is equal to our curve class beta. So this you can see by analyzing the tangent sheaf of this Hilbert scheme of curves. And if you have this property, you can see that. So you can see that this is the property that gives you the smoothness. The tangent sheaf would be a bundle, for example, with the tangent bundle. Okay, so these are the definition of the Hilbert scheme of curves and points. And then maybe some further properties. We have a diagram. In the following way. You have Hilbert scheme of curves and points that can get mapped to Picard of the original surface. It can also get mapped to Hilbert scheme of points, or it can get mapped to Hilbert scheme of curves. Okay? I will call this map points map. I will call this map determinant map. And I will call this map divisor map. This is the Morpher divisor map. So what do these maps do? Divisor map takes you from one of those one-dimensional subschemes of the surface to underlying divisor on S. We are looking at the schemes. These are not necessarily just divisors. They have non-reducible structure. So this one just picks out the divisor part of that one-dimensional subscheme. The determinant map takes you from the one-dimensional subscheme to, well, it needs to land on the Picard, so it gives you a line bundle which is defined by this divisor map. So it gives you a line bundle which is the O of the surface twisted by divisor map applied to that scheme. These are sheaf of functions having meromorphic poles along that divisor. And then the points map just forgets the curve part of the one-dimensional subscheme and spits out for you points. So this is taking you from Z and S to zero-dimensional subscheme. Zero-dimensional subscheme in S defined by, well, ideal sheaf of Z twisted by some divisor. Okay? All right. And then via this correspondence, you can see that it can be easily seen. It can be seen that from here we have the following properties. The Hilbert scheme of points and curves on the algebraic surface is isomorphic to Hilbert scheme of points times Hilbert scheme of curves. And again, I mean, this is not something which is new. If I give you a one-dimensional subscheme of an algebraic surface, I can look at the functions vanishing along that. That's not a bundle. It's a sheaf of rank 1. It's a torsion-free sheaf. And we know that torsion-free sheaves over surfaces, smooth surfaces, are always twisted ideal sheaves of points. This is that information. Torsion-free sheaf I of Z in here will always be written as some ideal sheaf of bunch of points, which are points being parameterized by this guy, and then things in here which are just line bundles. I mean, basically parameterizing the divisorial part of that one-dimensional part, subscheme. Okay, but we will discuss that further later. We can see it over and over through this talk. So then maybe I can fix some notation. This is extremely important. I mean, we tried to make the notations in these two articles kind of as simple as possible, but again, if one doesn't pay attention to the notation I'm introducing in here, it's very hard to follow. When m and beta are both not equal to 0, which is the case where you're looking at Hilbert scheme of points and curves on the algebraic surface, we have this canonical short exact sequence. So now I'm defining things. This is a notation. So let me first write it, and then I will tell you what that is. So this is some canonical short exact sequence that exists on there. So what does this mean? You have this Hilbert scheme of points and curves, and it gets, I mean, you can look at the product with the algebraic surface. There are two canonical projection maps to the surface and to the Hilbert scheme itself. This Hilbert scheme is a fine moduli space. It comes with a universal object. If you think of Hilbert scheme as moduli space parameterizing ideal sheaves of the actual subschemes, then there is a universal ideal sheaf in here, which I call Im minus beta. Okay? And this Im minus beta, fiber-wise over every point of the Hilbert scheme itself, gives you one of those one-dimensional subschemes in the actual variety S with the cohomological data that I just defined. Why is it I call minus beta? Is because, look at this short exact sequence. If you look at this is the universal subscheme itself. Fiber-wise, it gives you the Z's. This structure sheaf, fiber-wise, has the, as some sheaf over sheaf of OS modules, it has the Chern character something like this. 0 beta n. And the structure sheaf fiber-wise, the structure sheaf of this product, fiber-wise over every point of the Hilbert scheme itself, is just a structure sheaf of S, and it has Chern character like that. If you subtract them off, you can recover the Chern character of this thing, which is 0 minus beta minus m. That's why when I talk about universal ideal sheaf, I put a minus in here. This is extremely important for me in my notation. Okay? All right. Then when m is equal to 0, which is the case when we have only S beta, we have universal canonical short exact sequence again, which is similar. And these are my notations. When beta is equal to 0, which is for the Hilbert scheme of points, again we have this universal canonical short exact sequence. So these are my notation I will be using. And then this statement that I mentioned in here, of course, these objects, ideal sheaf of points, or ideal sheaf of curves, or ideal sheaf of points on curves, these are related to each other again by this correspondence. That every sheaf of rank 1 on the surface is given by the following way. So maybe a further note in here that, it can be seen from here that what I call I of m minus beta is isomorphic to I of m tensor with O minus z beta, O of s times s beta. O of the Hilbert scheme. These are universal objects, so everything is over the product. And so another thing notation which I would like to emphasize on, sometimes I will be looking at morphisms from some object like this to another ideal sheaf. But this part, which is the twisting by a line bundle, this thing is an invertible sheaf, so I can invert it and move it over. So when I have negative twists like that, at some point I need positive twists. So I could define objects like this too, positive beta. And for me, those are just ideal sheaf of points twisted by positive line bundle. You will see that these kind of things, these notations will be all used in my analysis. Okay, so these two notations are extremely important for me. So if you could pay attention to it, then you will not get lost. Okay, so that's that. And then our goal is to construct invariants for nested Hilbert schemes. Okay, so these are new moduli spaces. Over an algebraic surface, we can construct their virtual class and so on. That's our goal. So for that, first let me mention something. The remark, since S of M, the Hilbert scheme of only points on the surface, is smooth, then it has a tangent bundle. Tangent bundle T of S of M, which is isomorphic to homomorphisms, relative homomorphisms from universal ideal sheaf that I defined over there. There is no bracket, so I don't want to deviate from my notation to O of Zm. And by this I really mean the 0, pi lower star, R hom, I m. This is isomorphic to this as well. This is equal to relative x1. I keep putting brackets. I shouldn't, because I didn't use it in my notation. And pi in here is this map. Okay? So, this is a morphism in the derived category. This R hom without this is a morphism in the derived category of this product space. These are sheaves of all S times S of M modules. These are universal sheaves. And this is an object in the derived category of this guy, and I can then push it forward and take cohomologies. If I take the 0 cohomology, I'm just looking at homs really, but with a twist shift by 1, that turns into x1. Now, the reason I'm mentioning this in here, the natural deformation theory of Hilbert schemes, often, when you have, look at my notation over here, this is a story about this last line. Over the product of these two spaces, I have the kernel and the quotient. If you do, usual deformation theory for growth index cut scheme, which can specialize to Hilbert schemes and so on, you will see that the tangent space at every point of the Hilbert scheme is given by a morphism, all possible morphisms, from the kernel to quotient. Okay, so that's the natural deformation theory of the Hilbert scheme. That is this one. And the reason I'm emphasizing this particular one in here, this is just a definition, and this is what I would like to, emphasize. Hilbert schemes are these objects that come with two different derived structures. The two derived structures of Hilbert schemes are one being that it's the space parameterizing subschemes, whose deformation theory is what I just explained, and the other one is the one parameterizing sheaves, the stable sheaves, vanishing on those subschemes, whose deformation theory is this one. So Hilbert schemes have two different derived structures where the two overlap in the level of deformations, but not in the level of obstructions. So often when you can see calculations over cut schemes and so on, you see this description. Sometimes you see the other description. All of these invariant theories, they depend on the choice of obstruction theories. You can switch the obstruction theory, use something else. Probably you will be calculating some other invariant. But you're only allowed to do that if whatever theory you construct over that space matches, at least in the level of deformations, with the natural one. So these two guys, these 2 points of view are matching in the level of deformations, but not necessarily in the level of obstructions. Okay? That's what I wanted to emphasize. So just remember that natural Hilbert scheme theories are always theories given by homomorphism from kernel to quotient.
Sorry, but the two obstructions, like first obstructions, one maps into the other, right?
Yeah, that's right, but not isomorphic necessarily.
I mean, so in general, like one will just have smaller rank than the other. So
yes, that's right. I mean, if you pick the suitable obstruction theories nicely, sometimes you have a situation where for all the Hilbert scheme itself, the obstruction basically from here is x1i-o.
right.
You can see that that one embeds inside x2 that. And basically that embedding can show you that the one that you use with this one,
Right.
its obstruction sheaf will be a bundle, so you can use it for calculation of invariance. But this other guy with X1 has higher cohomologies. So it has obstructions to obstructions, but the other one doesn't.
I see. I was going to complain that it seems like one embeds inside the other. Only one of those theories should have like expected dimension 0. So
Yes, that's right. But there are also other theories where you even have smooth spaces which are obstructed, and then you can use different obstructions and calculate different invariants. So that's what I wanted to say. So it's more general than that. But yeah, you're right. In some situations, you don't even have an actual perfect obstruction theory, in which case you pick something which matches with the original guy in the level of deformations, but maybe with more suitable obstructions.
So this is something like reducing the Gromov-Witten theory of like a hypergeometry space?
Reducing the Gromov-Witten theory?
Yeah.
Not yet.
Okay.
No. 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 Okay. So this is that. All is, I think, I convinced you that we know a lot about Hilbert schemes. Now I define the object. So nested Hilbert schemes. I define it exactly the same way I did for Hilbert scheme. So suppose I give you this time a tuple n1 to nr, the vector n, and r bigger than 1 sequence of non-negative integers okay, and then suppose I give you a tuple of cohomology classes as well, beta 1 to beta. Now here is important. I want betas to run from 1 to r minus 1. Not r, but r minus 1, and there is a good reason for that. A sequence in second integral cohomology of the surface intersected with H11, so holomorphic curve classes, such that these curve classes are all effective for I between 1 and r minus 1. Okay. So given this data, now I can define the nested Hilbert scheme. So what is that? The nested Hilbert scheme is the closed subscheme okay, which is given by this embedding. I call it n beta, like that, and it sits inside S of n1, beta 1, S of n r minus 1, beta r minus 1, S of n r, right? Because we have r minus 1 many curve classes. The last one doesn't come with any curve class. Now, this is naturally defined by R tuples Z prime 1, Z prime R of subschemes of S, of one-dimensional subschemes of S, such that when I apply the points map, which I defined, points map takes a one-dimensional subscheme, so the configuration of curves and points, deletes the divisor, deletes the curve. When I apply the points map to Z prime I, it sits inside Z prime I minus 1 as a subscheme. For any I between 1 and R. Now this might be confusing, but let me clarify further. And I can, at the end, you will see that this is not something really complicated. So, remark maybe. Equivalently, S of n beta is given by tuples of subschemes. Now this would be clarifying. So what tuples of subschemes? Z1 to ZR. There are R of them, so these are point zero-dimensional subschemes. These sit inside S of N1 all the way to S of NR. And curves C1 to CR minus 1, which are points in this product space S beta 1 times S beta R minus 1. Okay, so it's a mix of points and curves together with such that together with maps phi from I of Zi to I of Zi plus 1 twisted by Ci such that phi is not equal to 0 map. Hence, necessarily, this map is injective. If you have a map between two stable ideal sheaves of rank 1, I mean, yeah. So hence, necessarily, phi's are injective. This is what a nested Hilbert scheme is.
Wait, before you said, why don't you allow beta to be 0? It seems like that case is already interesting and hard.
Yeah, beta is allowed to be 0.
Oh.
It's bigger than equal to 0.
Oh, okay.
Yes. And in fact, what we can, all of the nice properties, all of the nice generating series and so on are when beta is equal to 0. Good, thank you. So again, if you want me to even clarify further, let me just say something. You know, you have a system, pictorially maybe it is better. You have this algebraic surface. Let's pick R equal to 2. So twofold nesting. Inside this thing, we're interested in a moduli space parameterizing pictures like this. Maybe you have a one-dimensional subscheme. I mean, subschemes are complicated objects. I mean, they have reduced structure. So you can think of things like that. And maybe you have something like this. And this embeds inside here. So for me, this is Z2, and this is Z1. Z prime 2, Z prime 1. Okay? So this thing sits inside here, and then this guy, both of them correspond to ideal sheaves vanishing along these. So this is I of Z prime 1 and I of Z prime 2. And I like this to be sitting inside here. So that's why I'm looking at injected maps between ideal sheaves. Now, what's the point of having R minus 1 many curve classes but R many point classes? The reason is because each one of these guys, this is a torsion-free rank 1 sheaf on the surface. This is a torsion-free rank 1 sheaf on the surface. It's just a fact that a torsion-free rank 1 sheaf on the surface is an ideal sheaf of points. So for me, Z's without a prime, these are points. Z prime 1 is a configuration of points and curve, but Z1 itself is just points, as you can see. So this is just some ideal sheaf of Z1 twisted by some curve class D1, some divisor class D1. It's just fact. And this one as well. This is some I of Z2 twisted by some divisor class D2. All right, so these are twisted ideal sheaves. And if I have a map from I Z1 D1 to, this is T1, I Z2 D2, then I can do all the different things because these are invertible sheaves. I can put this over here. I can put this over there. So at least over there, I'm basically saying that I can think of this as D2 minus D1, and I call this thing, I want this thing to be an effective curve class, which I call C1. Okay? And I want the map phi1 to be injective. Now that's why, as you can see, when we are discussing the curve classes, because I'm looking at differences, for R many tuples, I get R minus 1 many curve classes relative, because I'm always looking at the differences. So that's why it's defined this way. But I think this now clarifies. What's this object? Any questions? All right. Okay, so this is the moduli space. And now I can discuss about its deformation theory, eventually construction of a virtual class. So deformation theory of S and beta, all right? So again, without loss of generality, let's assume R is equal to 2, because it's easier to study this thing. And let's look at this object again. So over here, I have, okay, so over here, with the corresponding maps, pi of S, maybe pi of n beta. Over here, I have universal objects. This time these are nested Hilbert schemes, so it's not just one sheaf, it's a complex of sheaves. So over here, I have a universal map from I of, if I put the twist on one of these, you can see, this is why this is nice, right? If I put the twist over here, then this is just an ideal sheaf of points, and this is ideal sheaf of curves and points. So object that I will get over there is something like this, going to positive twist I M1, M2 maybe, like that. So that's the universal family. And I like to obtain some kind of deformation space for that. Okay? So how do we do this? Let's do something. So we would like to know what are the deformation spaces if I like to deform this complex of two sheaves. It's just a fact from deformation theory. You can look at Hartshorne, you can look at Eduardo Cernesi, you can look at Iluzig, which is what we looked at, that if you like to deform an object like this, you need to deform this sheaf, you need to deform this sheaf, you need to deform the map. So its deformation space is governed by 3 different deformations. But that's hard to do. We need to do that step by step. What I like to do is, I like to fix one of these guys. So I'm one. Then just let this map and this guy deform. This is purely deformation theory argument right now. So some technique, imagine. I like to fix this one first. Find out what does it take to deform the map and the second object, and then add the deformations of the first sheaf to it. And that way I can compute. So let's fix, we fix I of M1 first and deform phi and IM2 beta. So why can we do that? So when does it happen that we are in a situation where this sheaf, we cannot just artificially produce a deformation, cook up a deformation theory argument unless this kind of thing makes sense. Where is the space where this guy is fixed and these two guys are allowed to deform? Here is that space. So consider the natural projection map. I call it points OPR1, which is the following map. So you can have the nested Hilbert scheme, beta. It naturally, you can apply the points map to it, delete the curve. That sends you to N1, N2, Hilbert scheme of nesting of points only. This guy, by my definition, sits as a closed subscheme inside S of N1, S of N2, and then you can project down to S of N1. Let's call this one PR1, and this is the points map. So I call this one P points, why am I the other way around? PR1, all points. So PR1, all points. So you can see that there's naturally a map from this nested Hilbert scheme to the Hilbert scheme of points. So let me write it down here again. There's natural map from here to here, which I call PR1 composed with points map. What is happening in here? Along the fibers of this thing, when you look at a point in here is given by one of the ideal sheaves. If I ask for you, how are the objects parameterized by the fiber deformed, They are exactly given by two-term complex of sheaves where this guy is not allowed to deform, but the rest is deformed. So that's my strategy. This is not something new. In algebraic geometry, especially in numerative geometry, we have heard about relative obstruction theories and so on. And the kind of a juice of this argument in here is that first, I construct a relative obstruction theory for this map, and then I add obstructions of the base, and I obtain the absolute obstruction theory on the upstairs. That's what I'm trying to do. Okay. And so, let's do that. So we would need to define deformation theory kind of in a rigorous way. So given, let's look at consider the following diagram. And I apologize for those of you, if you're physicists, I'm using some sort of algebraic geometry language, but this talk was intended to be for, more or less for algebraic geometers, but tomorrow's talk will be more physicsy. So you have this map, N1, N2, goes to S of M1, PR1, P points, and then I look at the map from some scheme U, and I call some scheme T. I call this map A, and then let's call this map G. I look at an extension of this scheme, square zero extension to T and T prime, and the goal is to construct a map G bar from here to here. What does this diagram mean? The bottom row of this diagram corresponds to U points of the Hilbert scheme of points. Hilbert schemes are moduli spaces. The very property of moduli space by its construction is that when you have a map of a scheme, this is a scheme over complex numbers, this is a scheme over complex number. However, this scheme is a parameterizing scheme. It's like a functor that you feed it with schemes over the complex numbers, and it gives you families parameterized by that scheme. If I have a map from U to here, naturally what this means is that every point in here will correspond to a point over there. So this map, what it means from algebraic geometric point of view, this gives you a U family of ideal sheets of points on the actual surface. So the bottom row gives us the U points of S of N1. The top row given by I of N1. The top row corresponds to families parameterized by T, corresponds to T points of Sn1 and 2 beta given by I of N1. So how should I write it? So maybe I write it as, so this also scheme theoretically is the same as these point schemes, Z1U. Remember that for Z without a prime, I call them points. So this is points with given length N1 parameterized by the scheme U. So these are given by tuples Z1T, and then C of T, Z2T, Phi of T. So theoretically, these are just I of Z1T goes to I of Z2T. Again, our map, C of T. And this is Phi of T. Everything is parameterized by the C scheme T. Okay, so this is the tuples that we are parameterizing over the algebraic surface. And so now, deformation theory has to do with the fact that suppose you're given a family parameterized by a scheme. Suppose you extend this scheme infinitesimally. A square zero extension means that somehow there's a canonical exact sequence where O of T bar, because this embeds inside here, structure sheaf of this surjects onto there. So you have something like this with some ideal. And a square zero means that J squared is equal to 0. That's what it means. And so you're infinitesimally extending the scheme that parameterizes your tuples. And your question is, if I do this extension, can I flatly extend this family to a family over T bar. That's the usual deformation theory argument. So question, can we extend this family IZ1T goes to IZ2T flatly to a T bar family. IZ1 T bar, phi of T bar, IZ2 T bar point, these are points in a curve. And analyzing this kind of question corresponds to completing the diagram like the following diagram. So remember that you have this thing, some square zero extension where j squared is equal to 0. And so now you can see how does it work. So if you have one of these families, you always assume that you have some extension family like that. And so your diagram that you will be getting is like, it's like you're having these two-term complexes and somehow you're tensoring them with this short exact sequence. This is maybe familiar for those of you who have worked with deformation theory of sheaves. So eventually you will get a diagram like this. We will get a diagram. We will eventually get a diagram the following way. So you have I of Z1T. This is phi of T. This is I of Z2T. And then this is I of Z1T bar. This is I of Z1T times J. What am I doing? If you like, this is a wrong thing to say, but if you like, take this thing, think about it as a vertical complex and tensor it with this exact sequence. And that's what I'm writing. So, okay. So there is the dotted arrows in here and here where F times J sits inside here. Okay? So answering the question whether or not there is a flat deformation of this complex to something over T bar is the same as answering the question, is there something in the middle in here as an OT bar module such that its restriction to O of T gives you the original complex or not? So if you can complete this dotted arrows into normal arrows, then you have answered the question. So Illuzi actually is the one who answers this question for us. So Illuzi tells us the following. There exists an element. He calls it the obstruction element, which is defined by x2 s times t co-kernel of phi of t, this is phi of t, to I of z2t times c of t times j, whose vanishing is necessary and sufficient to complete this diagram, to complete this diagram. If you complete this diagram, the T-bar families of objects that sit in here are by definition the T-flat deformations of the original two-term complexes. And Illuzi actually tells you that if you want to do that, there's an obstruction to complete this diagram, and this obstruction is this one. So this is why looking at relative obstruction series originally was a good idea, because Illuzi already worked it out in many pages of his book. So that's why we used it. And where F in our diagram satisfies the property that F times F tensored with restriction of F OS to T times S is equal to O of T bar, O of ST. Restriction to T modules is the same as I of Z2 T twisted by C of T. If you can find such F, then you have it. Now he also mentions that if obstructions are 0, then the set of isomorphism classes, isom classes of such diagrams makes a torsor under x1 s times t co-kernel of phi of t, and then I z2 of t c of t times j. If you're not familiar with deformation theory, all of this trying to say is that if you want to extend families parameterized by T of nesting of ideal sheaves inside each other, there's an obstruction to do that. So the obstruction spaces are given by x2, and the deformation spaces are given by x1. And when the obstructions vanish, the set of deformations make a torsor under this x1. So the usual deformation theory argument. Okay, so let me now that I told you about this, let me just write down our proposition. So proposition. There exists a complex. There exists a complex. Let's call it F dot, together with a map L dot N1 and 2 beta relative to S of N1. Remember that I wanted to construct a relative obstruction theory for that vertical map. So the vertical space, the space that is parameterized by those maps, that's this guy, and it has a cotangent complex. And for that, we are constructing an obstruction theory. So there exists a complex in here such that given by such that F dot dual is given by R hom pi co-kernel of the universal phi I n to beta shifted by 1, which defines a perfect obstruction theory for the map, or the relative map Sn1 and 2 beta relative to Sn1. Okay? So this is that complex. This is exactly what I wrote in here. Remember that I said x1 and x2? The obstruction theory, if you are not familiar with this is some object in the drive category of your space whose cohomologies give you deformations and obstructions. That's why I call deformation obstruction theory. And the point of this proposition in here is that there is such object whose cohomologies are given that. That's not hard to see. However, this object is perfect. Perfect obstruction theory means that there are deformations, there are obstructions, but there are no obstructions to obstructions. So this is the relative guy. And then, now out of that, we can cook up some absolute obstruction theory. So remember that we have this thing like that. And let's call this map, I don't know, I called it P, let's call it just Q, for example. Points map together with projection. What I can do is I can pull back cotangent complex of S1, S of N1. It naturally gets mapped to cotangent complex of the nested Hilbert scheme. And the difference between the two is the relative cotangent complex that I've put in here. So this is the difference. If you like, you can think of this as the relative cotangent complex, the definition of relative cotangent complex. If you pull back cotangent complex of this, it gets mapped to this thing. The cone of the two objects in the derived category is some complex, and that's the relative cotangent complex. Now, what are we doing in here is we have constructed something. This is space is a smooth. So this guy comes with a natural, this actually is a smooth, this is just the cotangent sheaf. So this is just cotangent sheaf of SN1. For this guy, we have obtained a map which captures deformations and obstructions of objects that we are interested in nicely. And for this one, we are looking for some object together with a map. And how do we do that? We can basically use this exact triangle to construct it. So what this is, we can put it over here. We can shift it by 1. We can call this map G. If I take the cone of G, I can take the cone of this map G and put it back in here. So cone of G minus 1. This way I can obtain some object in the derived category of the guy upstairs. And then I can discuss, does this thing capture deformations and obstructions of these guys correctly? I can try to see if that's the case. And I can try to see if it doesn't come with higher cohomologies. And if it is, then that's the perfect obstruction theory. And that's what we do. Okay. So all of this I will put as a theorem. By the way, maybe it is worth mentioning in here. Let's make a remark. Let's look at this nesting of ideal sheaves inside each other. Maybe this is worth pointing out. This guy sits inside positive twist of this guy. I call this map phi, and I call this one co-kernel of phi. Okay? And my obstruction theory that I just mentioned had this property. So f dot dual was some r-hom, some difference of the co-kernel of phi and I n2 beta, shifted by 1. This was our relative obstruction theory. Now let me mention this. So if you apply r-hom blank I n2 beta to this, then you realize something nice. You can see that you will get first this guy. You will get r-hom co-kernel of phi I n2 beta. Then you will get r-hom I n2 beta, I n2 beta. Then you will get that term, I n1, I n2 beta. And then you will get r-hom. This repeats again, co-kernel of phi I n2 beta shifted by 1, which I called f dot dual. Maybe the fact I would like to emphasize is that now when you look at this, as you can see, the morphism between the co-kernel, the difference of the two ideal sheaves, and I of n2 beta, is the co-kernel of the morphisms between these two. So from here you can see that f dot dual with that description is also the same as cone of this map of r-homs. R-hom I n2 beta, I n2 beta, with the map to I n1, I n2 beta. Now why is this interesting? Because remember that I told you when I fix I of n1, I need to deform the map and I need to deform I of n2. This is the deformation of I of n2, and these are the deformations of maps. And you need to look at the difference. So you get the deformation obstruction theory, the relative one. So it just makes sense with our intuition. And guess what happens if I add this omega to this story? It's just adding deformations of I and 1 and 1 to the situation. So that basically should be sitting over here, right? So theorem. So this is with Gholampour and S of n beta is equipped with an absolute obstruction theory, absolute perfect deformation obstruction theory, F dot, which comes with a map to the cotangent complex of this guy, where the dual description of F dot dual is the following way. What I just said, it's the cone of adding all of the sheaf deformations and then subtracting off the deformations of maps from them. So I from 1 to R, now I can do it for general case, R hom pi, this is relative R hom, I of Ni, I of Ni. I need to take some trace free over here. Don't ask me why. It is. I'm not going to get into that. But then when I look at the difference of these guys, R minus 1, many of them, R hom pi, I of Ni, I of Ni, beta I. Yeah. And pi here is just the map to the moduli space. Okay? So add all of the sheaf deformations, compute all of the map deformations one by one, and look at the difference, and that gives you the deformation theory you want. This is our theorem, and we proved that it's a perfect deformation obstruction theory, and many more things. This was somehow an interesting object for us, because first of all, corollary from this obstruction theory, we can construct a virtual cycle. One can construct a virtual cycle, virtual fundamental class, so this is an element of the Chow homology of the Nested Hilbert scheme, sitting in some degree, and of course, because the construction is just consistent, this degree is exactly the expected dimension of the Nested Hilbert scheme. So this is the expected dimension of S of n beta, which is equal to, you can do growth in degree Monrock theorem, and you can calculate this thing. So this is sum of ni's, are many of them, minus I to r minus 1 of beta I times k minus beta I divided by 2. That's what it is. And what is k is this first Chern class of the canonical bundle of the surface. It's the canonical class. Canonical class. So this is the expected dimension of the Nested Hilbert scheme. And tomorrow I will tell you about the generating series that we calculate over these things. It's remarkable that these generating series, in some cases when we are looking at nesting of points, they are given by modular forms. This is remarkable. Their modularity, when I talk tomorrow about the threefold geometries, actually induce and tell you information about modularity of some known theories, like Sabri-Witten theory of surfaces, Donaldson-Thomas theory of threefolds given as local surfaces, even correspondence between those things. This is sheaf theoretic correspondence between Donaldson-Cyber-Witten theories. It's just a holomorphic version of it. But also, as just purely a surface theory, this is interesting because you can see that physicists always, when they do quantum field theories and so on, they have these fields and B field and whatever. I like this when physicists do it. Like they say, we turn off this field, we turn on this field, we get some theory. We turn on this, we turn off that, we get some theory. Here you can do the same thing. You can turn these things on and off, and it just turns out that this deformation obstruction theory actually covers all of the known deformation obstruction theories of previous theories. For example, so maybe this is the last thing I would like to say, if I can borrow from you some 2 minutes. So some special cases. I just mentioned it. Let R be equal to 2, first of all. So let's turn off beta. If beta is equal to 0, then we are dealing with nesting of points. And in fact, it just turns out to be that if you would like to have ideal sheaf of points sitting inside each other, n1 should be bigger than n2, of course. In the curve case, it's not the case. If there's a curve there, injectivity of that map is just determined by Riemann rock or whatever. But in here, you can easily see that. So in that case, our theory spits out a virtual cycle for this one. So then the virtual class of this guy would be an element of A based on that formula, n1 plus n2. And now we can ask, even if n1 is equal to n2, our spaces are smooth, and our obstruction theory virtual cycle will just give us the fundamental cycle of the Hilbert system of points, because this is a smooth space. So that's one thing. Of course, it's a good check. If n1 is supposed to be bigger than n2. So if n1 is different from n2 by 1, then that space again turns out to be smooth, which is some classical result. This is the result that before this paper we knew about nested things. That's the only thing that we knew. Nesting of points when the gap between the points is equal to 1. Again, in that situation, S of n2 plus 1 n2 is a smooth. And it's we can calculate the cycle. You can see these things in our paper. So we calculated this, and we saw that it matches with the fundamental cycle of this guy capped with C1 x2 I of n2 I of n2 plus 1. This is the co-kernel thing, I of n2. This is a formula. This is a formula for virtual cycle, basically. And this matches with the earlier results on nesting of points with gaps of 1. What else could we do? We could turn off both point classes. If this is the case, then in that case, our Hilbert scheme is just Hilbert scheme of curves on the surface. And in that case, our obstruction theory will be just R pi over star of O of the universal subscheme twisted by itself. And again, there is a paper on this thing, Okonek and company. So Dur and Kabanov-Okonek, they have this paper in the topology, journal topology. They constructed an obstruction theory for these things, and we will cover that too. By just turning off n1 and 2, working it out, we can see this exactly our obstruction theory reduces to theirs. If you, maybe more interesting example, if you can do many things. If you turn off n1, but let n2 and beta both be not equal to 0, then in that case, you're looking at a S0 n2 beta, which turns out to be Hilbert scheme some relative Hilbert scheme of n2 points on this universal curve over the Hilbert scheme. And this is something Poincare and Thomas studied. So this is the stable pair moduli space. So this is pair moduli space, beta plus beta k divided by 2. This is the stable pair moduli space, the stable pair space of Poincare and Thomas, as well as Poincare's student, Ben Baker, right? Ben Baker studied this as well. Baker. And again, our obstruction theory covers that. It becomes equal to that. So we can see that in that situation, f dot dual will be equal to some O of S 0n beta times S together with a map. Oh, sorry. So we have this object I dot, which is the universal stable pair over the moduli space, and our obstruction theory f dot dual becomes R hom pi I dot f. This is for those of you working on Donaldson-Thomas theory, this is again familiar. And we can reduce these theories as well. We have realized that, again, it's in the paper, Kool and Thomas are working on geometry of threefolds given by local surfaces. They have defined local stable pair theory of a threefold which is given by total space of some line bundle on a surface. They have this notion of reduced stable pair theory. Again, our Nested Hilbert scheme obstruction theory covers that. So it looks like this is a nice object to study because it relates all of these known theories to each other. And tomorrow you will see that it has even further properties. Like you can calculate their generating series and so on. And I saw in here, sorry to go over.
Questions? Comments?
Yes.
So I know maybe you'll say this tomorrow, but can you briefly describe in what cases you can calculate?
Yeah. So in case that we can calculate is just nesting of points.
Okay, so no beta.
No beta. In no beta case, the reason is because when I have this kind of thing, the geometry is still the same. This is a closed subscheme embedded inside here. But the nice thing about here is that these are smooth spaces. When there is beta, bottom of this or that, these are not as smooth necessarily.
And can you do it for arbitrary R or for 2R equals 2 or?
For arbitrary R, you can also do it. But the calculation that we have put in the paper is for R equal to 2. And for nesting of points, the idea is that somehow you can see that, right? This is sitting inside here. And you can think that if this was smooth, which is not, if this were smooth, when the gap is 1, it has a normal bundle in here. And so the virtual cycle of this one literally is given by the top Chern class of that normal bundle capped with fundamental cycle of this. In this particular situation where this is singular, it has a virtual normal bundle. And actually that's what we do. We construct that virtual normal bundle on here, some object in the K-theory of the product, take its Chern classes, integrate it over this thing, and then show it is equal to.
And is there some class of surfaces for which you can calculate, or for any surface you can calculate?
Yeah, for any surfaces. So no, yeah. So it needs to be for reduced theories. There are some things that I didn't mention. Like for example, if the arithmetic genus of the surface is bigger than 0, our virtual class vanishes. Then we need to reduce it. In some cases, we need the surface to be symplectic. In some cases, H1 of the OS needs to be 0 and things like that. But all of that is in the paper. Yeah. For Fanos, it works. Yeah. For example, for all toric projective surfaces, it works. We can prove that actually our generating series, in this point case, our generating series is eventually, we can prove a formula, which is very important, that somehow, I mean, the story is that over here we can define the invariance, but we cannot calculate anything. We need to calculate things on the ambient smooth space. And in order to do that, we need to show that integration of something over here is the same as integration over here. So we prove it for toric surfaces, and then we use Levine-Pontripanti cobordism argument to say that if it works for P1 times P1 and P2 and things like that, it will works for all smooth projective toric surfaces. So for those things, we have formulas actually. Yeah. But tomorrow, that's the topic of tomorrow. Basically, I can prove it. Yeah.
More questions? If no more questions, let's start Artan.
Thank you again.
Did you press?
Yeah.
So tomorrow is in the science center.
What?
No, I said tomorrow will be in science center.
Yes, on the side.